Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Vilson, who has finished one of our courses, ROS Basics in C++. And at the end of this course, there is a project that teaches you about the main components of ROS Basics and allows you to implement it in a real robot. So that's what the project is about. And today we have Vilson to show us what he's done. So hi, how are you, Vilson?
Hi, I'm well.
Great. I'm excited to see what you've done with your project. So whenever you want, you can start sharing your screen and just show us what you've done.
Okay. Can you see the
Yes, I can
presentation?
see a presentation standard value.
Yes, I will start right now. So just to explain what I'm doing for the service, the first part of the project is make a service to make the robot find the wall. So for that, I'm getting 60 samples in a range in front of the robot with the front laser. With the LiDAR, and I'm projecting all these 60 samples into the x-axis and calculating with that the standard deviation of these values. So I can make a good differentiation of an obstacle, a wall, or something like that.
Nice.
And then with that, I can use this logic here. After testing a lot, I realized that if the standard deviation value is bigger than this threshold value, 0.02, about approximately, it's an obstacle or you are not facing a wall.
I see.
And I'm putting a condition for the forward distance too. So I don't want to take the walls too far away from the robot. I want to get the closest possible.
Right.
So I put in this condition too. It's this value 1 meter is after testing a lot, and then this parameter I can be sure that in any position of this circuit of this environment we have, the robot can find some wall in 1 meter distance, and he's not going to take a wall too far away. Then, if any of these conditions, my standard value is bigger than this threshold, or my forward distance is bigger than 1 meter, I will have the robot turning clockwise until he finds a condition that suits him. So once he finds, he's going to approach the wall. So the robot will find the wall, and then he needs to align to the wall. For that, I'm creating this variable minimal distance that I'm calculating the distance from the wall. It's I'm sending him to stop approximately 30 centimeters from the wall, and then I create this variable minimal distance, and then he's going to rotate until my right distance calculated from the LiDAR is equal to this minimal distance more a tolerance. This tolerance I need because you have variations in the sensor measurements. You have some slipping while he's rotating, so you need to sum this value.
Right.
So let's see this working. I know. Can you see the ROS
Yes,
ject?
I can now see the robot and your ROS ject, yes.
Well, just 1 second. I did not launch the bridge. Here, I feel comfortable for interrupting me and make some questions if you want.
Great, thanks.
Is something that
Yes.
It's not very clear.
At the end, I'll ask him questions, but yes, thank you.
Okay, so the bridge is launched, and then I'm gonna launch the main package, and then here you can see he's really, really close to an obstacle. And if I use it just the logic for the minimal distance, he's going right away to this obstacle.
Right,
But
right.
I
I
hope,
was gonna say you're starting with a difficult starting position.
yes, here we can see that I'm creating for
Ah,
distance, standard deviation, and what he's doing, he's turning clockwise. So here he got really low standard deviation, but
but
the
really
forward
far.
distance was
Ah,
bigger than 1 meter, and now he's turning, and I hope he finds that wall over here.
so it's a combination then between the distance and the standard deviation.
Yes, exactly. And now he start moving forward.
Very perpendicular. Nice.
Yes. And now he found the wall. I initialized the minimal distance variable, and now he's going to turn counterclockwise
Mm-hmm.
until that condition is fitted. So now, okay, he's starting the action right now that's publishing my current distance, my feedback,
Mm-hmm.
each second, and the wall follower node that makes he keeps moving alongside the wall.
Right, and the service ended the moment it got parallel, right? After what you explained.
Yes, yes.
Uh-huh. Oh,
I
that's
I end
nice.
that service,
That's
and now he's saving every each point, right? He's going
uh-huh.
to print at the end.
That's a really fast blap there.
Yes.
I'm impressed. Fast and furious a little bit. I like it.
I was almost in the limits of the
Uh-huh.
robot.
I was
You
gonna
let
ask.
us to
Yeah,
control.
because sometimes we have a protection that kills the velocity. So you've definitely found the limit there.
Here,
And then now it's
it,
done.
yes, I'm printing for you all the data sample, the
Yeah.
number 1, 2, the x position, y position, and theta already in degrees, the z-axis. And after I just kill the node, and that's all. And here you can see like the current distance. It is
That it traveled. Uh-huh.
5.9 meters. So I think that with the system is pretty much what I have to show, and then I can show the code a little.
Yes, yes, please. Just to no, we don't have to go
Yeah.
line by line. Just to get a general sense of how you
Okay.
did each part. For example, I think your method for standard deviation plus the distance is great. So kind of like just show us little interesting parts of your code.
Okay. Here are you seeing the code?
Yes, I can see the fine wall
Yeah.
server CPP.
Standard deviation.
Yeah.
Okay. Here, the first of all, I'm calling the topic callback here to set all my variables, all my laser range into this vector.
Mm-hmm.
And here, just a trick thing, because you with the LiDAR, you receive many infinite values when something is not pointing right away, it's not receiving the value back, and that kills completely the logic. So if I have bigger than one value, I just stipulated here 10 meters. It's never going to
Right.
take
It's
10
in this
meters in
case.
this environment. In this case, I'm going to put 10 meters here, or else I'm going to put the real value I'm receiving, just so the method works well.
Uh-huh.
And then here I have these conditions right now. I'm initializing the cosine vector, the vector with all cosinus. And then I have the first while, that's find the wall and approach the wall. And here we can see exactly what I said, that if the standard deviation method here is bigger than this threshold, or this forward distance is bigger than 1 meter, he's going to turn clockwise. Here, okay, he's going to turn clockwise. Else, he's going to move forward, and then move forward until your forward distance is bigger than 30 centimeters. Then you stop.
Right.
Else, you can stop and the robot found the wall. And here's something interesting, because I needed to, these functions, they just set the values. They don't publish the velocity. So I need to publish after, and I publish for a while, and then I stop the robot for a while, because the times that I try to implement without stopping the robot right away, the robot overshoots the condition.
I see.
Then I make him turn for 1 second or move for 1 second, and then stop for half a second, just to be sure he's going to account all the measurements. And then add the condition to line up. So here, after I find the wall, I'm initializing this minimal distance. And then if the right distance is smaller than minimal distance, more a threshold, a tolerance, sorry, the robot is found is at the right place. I can set the response to true and stop the robot. Okay, or else I'm going turn clockwise. It's pretty much with the service. It's pretty much what I have to show. And then there is the logic for the action, just to show how he knows how to come back to that region to stop the node completely. So first of all, I'm initializing two variables, lap and exit from start. Then he is at this is the first, the initial point of the robot, the initial condition is going to start moving. And after he gets out of this start region, he's going to set exit from start equals true. And then he's going to complete the lap. He's going to keep moving until he approaches the initial point again. And when he's entering into this end region, he's going, and my exit from start is true. So he's coming back. He already go away from this region. I will set the lap for true, and we'll kill the node. We will stop the system. Going set the action response to true, and that's okay. Okay? Okay, just to show quickly right here. This is my action server. Here, the important things, I'm setting these two variables, creating these two variables, point 32, geometry message. This is my actual coordinates. So the coordinates I have in that time. And this is a vector of these variables that I'm going to storage every point I'm passing through.
Yeah.
So right now in the top callback, I'm creating quaternion message just to storage all the quaternions, because I'm receiving quaternions from the odometry, and I have to pass to Euler angles to calculate the yaw. And then I'm calculating my actual coordinates. This coordinate z, it's not correct because he's getting just the quaternion. It should get yaw, but I'm going to transform that later.
And the important ones are the x and y in reality, because it's the graph of the path, honestly, that we're interested in. And then I'm going to set these variables that I showed before, lap and exit from start. While lap equals false, I'm going to run this. I'm going to transform into this variable angles that's struct here. I created just to store raw, pitch, and yaw. Raw and pitch are not important here, but and then
I'll go and transform Quaternions to Euler, and then make my z actual coordinates point z at the right value, already in degrees. So then I'm going to push back this message here, actual coordinates, into my vector of 0.32 geometry messages. So after that, I'm calculating the delta distance, so the distance between two periods of time, 2 seconds. Well, what is the distance I move it? So I calculate the distance from the point I am right now and the distance, the point I was, that storage in this vector. And then I'm gonna sum with the current distance I already have and publish the feedback. So that's all. And then here I'm checking if I already got out from the starting region and if I already come back.
Right.
Okay. Then I think the last thing is just the wall follower, the main logic about that. Now I have these three main situations. That's when the robot is getting too far away, 30 centimeters away from the wall, you're giving some angular velocity to him. Alongside this linear velocity, he keeps moving positive. If the robot is too close, you're going to make he's going far away from the wall, giving him this angular velocity. And if he is in the right place, between these regions, you can just make it going forward.
Right.
But I put another conditions here. When he turns left, I need that when he's facing a wall, when this distance is smaller than half a meter, he's going to have a really big angular velocity. That's why he's going to have that
the strong turn, yeah.
Yes, the strong turn. Exactly. The hard turn, it's another condition when he is actually facing a wall, like 15 centimeters, 10 centimeters, he's going to stop the linear velocity and just rotate. Right. To get out of this situation. I realized that it was important when you start your whole package, your service to call the row, to find a wall, to close a wall. So if he starts too close to a wall, he could start moving forward too close to a corner, because he can align with the first one and face another. So you need to set the velocity to 0 and make him rotate. And then another one, that's when I'm facing an obstacle, when I have an obstacle in the left side. So I'm going to have a turn into the middle, just to be sure he's not hitting something there. And then, to show, this is the main file that it calls the service, it calls the action, and it runs the wall following. First, I made a class with the wall following and the action client here. Here I'm initializing all variables, making the callback groups, and then here I'm just putting that logic I showed right now.
Right. Yeah.
To the movement. Okay.
Sorry to interrupt. 5 more minutes.
Okay. And then here I'm plotting everything from the action. After plotting, I'm creating this message just to set the velocities to 0 and then kill the node, because I'm not using him anymore. And this is just the service client I'm calling here, making this class, and then calling everything in the main. So the last thing is I made uh, the two main service methods. I think that's from the near distance and with the standard deviations, and I saw some advantages and advantages with the
Mm-hmm.
method I showed you. The first advantage is that you need to know very well the environment and test a lot to turn that parameters. And I don't know if in any environment it's going to work well with this logic, but you
Mm.
can improve it. And if the robot is already in the right position facing to a wall, he's going to turn and then turn back.
Right.
So you lose some time. And it may not find the nearest wall. So if you have a wall that's you're facing a wall and it's like half a meter, but there is another that's 30 centimeters. If he finds first the half a meter, he's
Right.
going
It'll
to
go
that
to that
one.
one, but it'll go to a wall. That's the kind of
Yeah, yes.
advantage. Okay.
And and then the advantage is yes,
Right.
you
Okay.
can
Yeah.
differentiate the obstacles from a wall. That's pretty good and works in almost all positions of this environment. In this test, I tested in almost every place there, and it worked in almost every place. In every place I tested, and it may not find the nearest wall, but usually finds the quickest because moving forward is quicker than rotating for
Right.
this robot, for this logic. So I think that's pretty much what I have to show.
Awesome. Well, really nice. Congratulations, Vilson. Do you mind stopping sharing your screen so we can
Okay.
kind of go to? I just have really, really nice project. Congratulations. By far, what I think is the coolest thing you've done is this ability to recognize between a wall and an obstacle with such a simple strategy.
Yes.
I've seen a lot of people. This is not a required part, so it's like an extra step you've taken to recognize an obstacle versus a wall. And I've seen many ways to try and tackle this, but this is a really really simple and easy way. My question here is, how did I know you found that standard deviation above 0.02 or something, that was your sort of threshold. So my question is, how were you looking for that number? So you were kind of seeing if it was going to the obstacle, and then seeing what the standard deviation was in that case, and then, or how was the testing procedure so you could achieve to 0.02 and not, I don't know,
Okay.
50 or
Uh,
something?
I was just was launching the first the simulation and then using the keyboard, the controls for
To see the
tele.
standard.
Yes, exactly. I was facing every point I could, and then, oh, this is a wall. This far away from a wall, the standard deviation changed a little. He
Mm-hmm.
can notice that's still a wall, and then if I turn to this obstacle, he can notice. So I was testing many points and then catching the results and
Right.
thinking about that.
Okay, nice. Cause yeah, I think it's this one of the simplest ways, and it looked like it worked really well. So that was awesome. I also really liked, you obviously have experience with C++ because your code was very structured, very nicely, very so you can tell. So it's always nice to see. And let me ask you. You said that you needed to stop the robot during the service. Like you had to make it go forward for like 100 milliseconds or something, and then you would
Yes.
stop it. Why do you think that is? Maybe it's like a blocking situation. Did you have a call multi-thread executor in the service part, or why do you think that was happening? That it would overshoot.
I do have this move threading,
Mm-hmm.
multiple callbacks right here, and I may be thinking that I was trying to make it too quick.
Maybe the
And
rate, yeah, maybe the rate of
the
the
rate I was
callback.
using, and then he's not updating
Right, right.
fast enough, and I think that may be that, but I really don't know the main reason.
Yeah, because
I'm not sure.
so it might be like the rate of a callback somewhere, or maybe the rate at which you're spinning that node that is doing it
Yes,
at maybe.
because the rate of the callback is like I think for the here for catching the topic here, I but here it's like 15 milliseconds. I know it's not exactly
Right.
15 milliseconds, but it should be higher enough, I think.
Yeah,
Then
yeah.
it's
Well, that's something
uh,
to think about because you're right.
yes, that's
It looks like you've done
uh,
everything because it wasn't overshooting, for
in,
example, in the wall following, correct? It wasn't going like
yes,
that. You
exactly.
noticed that it went all the way over, or that
And
it
and
did the
it
hard turn early.
and for the simulation, I don't need this part. I don't need.
Okay.
It works pretty well, but it's that's why I think it's something with the rate of update of the LiDAR,
Right. Or maybe
maybe.
the rate of, yes, you're right. Yeah. And there's also a difference between the simulation and the real robot
Yes,
that you
yes.
have to publish at a rate for command val. I don't know if you noticed that if you try to do like a ROS topic pub, like a ROS 2 topic pub of command
Yes.
val, just a message, in the simulation, I believe it just keeps going because it keeps
Hmm.
receiving this. But in this one, it has kind of a safety that you have to publish it at a certain rate. So maybe
Yes.
that also has something to do with it. But
This rate high right here, right?
yes.
Well, I don't know why this.
But anyways, that's
Yeah.
just something to think about. But you found a really good way to mitigate it. I mean, it looks
I
like,
try I tried to increase this rate right here, but it didn't work.
oh, all right. Well, eh, those were the points that kind of stood out to me. But again, it's a really nicely done project and accomplished the tasks and even went further with that great tool. I might take some inspiration in some other code I've been writing to think about a little bit of this method. So thank you so much, Vilson, for showing us your
Thanks a lot.
project. It was really nice. And
Thanks.
congratulations. And for everyone else that is watching, you can do what Vilson did here and present your project after taking our courses, and you'll be able to obtain a certificate from us of learning. And this is the last step to make sure we are offering something that actually makes people learn. So again, thank you, Vilson, and I hope we see you around for other things.
Thanks, Rodrigo.
All right, guys.
Have a nice
That's
day.
that's it for us, you guys. We'll see you later. Bye bye. All right, cool.